So we finished the quiz. Today we're going to work on interest factors in Chapter 2, continuing on that. But let's look at some announcements. I've posted on iLearn, probably some of you get the alerts from iLearn, about our classroom location. We're going to, on Sunday, meet in EB2 104. So that'll save you having to climb up the stairs. We're going to be in the computer classroom. And we'll probably be in the computer classroom for a couple of next week's lectures. But for now, let's just focus that Sunday is going to be in there. So please be on time. I think that one even has a door that locks. And so, that'll make it even easier for us to distinguish who's here on time and who's not. Homework 4, I gave you the physical paper for that previously. The PDF is posted on iLearn. That's due on Tuesday. And we're covering the material now that is included on that assignment. Feel free to stop by my office if you've got questions. If you're working on it over the weekend and you've got a question, you can send me a message and I'll do my best to respond. Although I don't take all of my books and notes home with me over the weekend, sometimes it's a question I can just answer off the top of my head. So feel free to send a message if you've got a question. Any questions before we move on? All right. Here is a table of factors and equations that we're going to see on several future occasions besides just today. This is included on today's in-class exercise, although unfortunately I didn't make it large enough because some of these equations are pretty complicated, and I've been glad when some of you have had the reflex to, instead of looking up the factors, you can just solve for the amounts using the equation pretty easily. Like for f/p and p/f, those formulas are relatively simple. But then when you have to do a uniform gradient present worth, in other words, convert from g to p, and you'll find out today what a g is, but you just look at the complexity of that equation, it's a little more time consuming than just looking up the factor in the back of the book for a certain I value. So sometimes you'll just want to use the equation, sometimes you'll want to use the factor, and sometimes you'll have the flexibility on an assignment to choose whichever method you prefer. But then oftentimes I'll tell you, do this one with the factors, do this one with the equations, and it'll be clear what approach you should take. But I wanted to show this to you, and I'll post the full screen version of this on iLearn so that you can print it out if you'd like. And there's a similar table of equations in your textbook so that you've got a printed resource there as well. So here is the in-class exercise for today. Before we get started on it, we're going to do just there's a question on the front and then some stuff on the back. We're going to split it up into phases. Just do problem 1 first, and of course you're going to be working together and we'll take a look at the solution. And then before you start on problem 2, I'd like to talk about interpolation and gradients. So just start on 1, and you can glance at 1 and 2, but don't start on those until we've had a chance to talk about the underlying material. Oops, sorry. All right. There we go. Papers. We spread those out. All right. By the way, the 8% table that you need for the last question is on the back side of the paper. All right, let's gather together our brains for just a moment and let's take a look at some new terminology. Discount rate. Okay, so you'll be paid 50,000 dirhams in 7 years. What's the present value of that payment for a discount rate of 8%? Okay, you're still going to use the same formulas and the same table lookup factors as you have before. But here, instead of saying an interest rate of 8%, we're saying a discount rate of 8%. And the reason for that, remember, is that when you move money from the future to the past or into the present, when you're moving money backwards, in other words, it's worth less. Remember that if I give you 1,000 dirhams in 7 years, it's worth less than that today. And so we call that process of moving money backwards in time, we call that discounting. And so that's why it's called a discount rate. It means just make it smaller at the rate of 8% per year. Okay? So that terminology, I'm glad that some of you picked up on that and were wondering exactly what it meant. All right, so let me pull up the solution for this one. All right, so if we summarize the equation according to the bracketed method, we say it's a P/F. So find the present amount given a future amount that's known. That's the interpretation of P/F. The unknown is first, then the known is second. I equals 8%, N equals 7. All right. So what would we have done if it was monthly compounding? Then the number of periods is 12 times as much, and the interest rate is 1/12 as much. But here, it was annual. Okay, the formula, 1 plus I to the negative n power, that's what we see when we look here on this microscopically small table that I provided. All right. So you can calculate the factor based on this. This is like your own factor, and this factor is the ratio of P to F. So it means the present value is 58% of the future value, 58.34904%, and so on. Now, the advantage we have of calculating this factor our own is that we can take lots of digits of precision. And in fact, I kept all of the digits in my calculator, even more than I wrote, so that I was able to express the present amount, the present value of that, to a lot of digits of accuracy. If you look on the table lookup factor, it just has 4.5835. Now, that's not different than what I calculated, but it doesn't have as much precision. So 0.5834904 and so on. So when I use the table lookup method, I calculate 29,175, but really what I have to write, and I corrected this on my paper, truly what I know about P is it's only 29,180 because I'm forced to round off this fourth digit, and since it's a 5 here, we round up. So how would I express the answer when I'm using the table? I'd say 29,180. But I know using the factor method all the way here to the 100th of a dirham. So any questions about precision in the back? Mm-hmm. 1 minus 0.08? Mm-hmm. Yeah. You didn't get the same answer, right? It was somewhat different. It's because, well, you could take the inverse of this, but if you're earning 8% every year, it compounds differently than if you're losing 8% every year. It's a proof maybe a little bit lengthy that I'd have to show you in my office, but it's because of how it compounds. If it was just a single year, it would be the same. But because it's compounding every year, then it's not the same. Yes? Why? It's because when we looked up in the back using the factor, if you look on the back side of the page, it says 0.5835. So if we write all of these digits, we're claiming to know things that we don't really know. It's sort of a level of precision that the factor doesn't give us. The factor is just rounding it off to 4 digits, and so that means that you should round off your final answer as well. I could have, for example, I could have said how many fills it was, but that wouldn't have been accurate. You can't calculate exactly how many fills should be paid if you only know the factor to 4 digits in this case. All right. So question 2 and question 3 are going to have to do with interpolation and with gradients. So let's talk about interpolation first. What we have sometimes is an interest rate that is in the middle of 2 factor values that we can look up. If you do the formula method, it's easy to find the correct factor. You know, it's just 1 plus I to the n power, and you get your factor. But if we want to interpolate with the table, and this isn't the only time we're going to interpolate for this semester, what you do is you're sort of finding a weighted average in between 2 values. And you can think of it this way. If on one axis we have the percentage rate, so here's 8 and here's 9, then the value that we had for 8% is 2.1589. So here's 2.1589. And then for 9, the value is 2.3674. So here's 2.3674. Assume a linear trend between them as a simplification. It's actually not linear between them, but it's okay to estimate just for simplicity that it's a linear. So what we want to know is if our interest rate is 8.3, then what is going to be the factor that we should use? Factor. All right? So does anybody know how we're going to interpolate, like how you can find out? What's the approach we should follow here? Yeah? All right. So you're saying we should look at the slope. Exactly. So once we know the slope of this line, we know how much extra factor we get for the additional 0.3 of interest. So we know that the factor, that we're trying to find the factor for 8.3. It's going to be at least 2.1589. But then it's also going to be some extra, right? So the 8 gives us 2.1589, but then we need to find the slope of the line and multiply that by 0.3 and then add the amount to our baseline that was the 8%. Okay, so that's all the hints I'm going to give you on that one, and I'll ask you to do the calculations in just a moment. Before I turn you loose on it, though, let's also talk about gradients. Gradients are weird. They're really weird. Think of it this way. What if you had to start paying an amount and it was always more and more and more that you had to pay? It kept getting larger and larger. So here is the typical form of a gradient. What it shows is that we're going to find some present equivalent of it. But the form of a gradient is that in the first year nothing happens. And so 0G is what we call it. In the second year, you have to pay a certain amount. That's the first G. So the amount here is, maybe it's 100 dirhams, maybe it's 1,000. It's just a certain amount. In year 3, you're paying 2G, so double the first year. In year 4, it's 3G, and so on. And so the pattern of this is that it doesn't continue infinitely. It continues for n years, whatever n is. If n is 4, then this would be what it looks like. If n is 5, then there would also be a 4G that we have to have. So the key tricks that I have to remind you is that year 0 of the G, year 0 of like our time view here, the first year also nothing is happening. And so the most common mistake that students sometimes make is that they accidentally label year 1 as year 0, when really year 1 has nothing because it's 0G. So these gradients are kind of rare, but occasionally there are situations where the structure of the loan is such that the bank would give you a little bit of breathing room so that your business can grow and you don't have to start making the payments immediately. But then over time, your payments get larger because they know that whatever equipment you've purchased is more productive and your revenue is growing. So that's an illustration of how maybe a gradient would be imposed. So this form of it, you can see that there's a present value that's positive and then the gradient is negative. You could flip that. It could be that you have to pay now and then over time you're going to have an inflow to you that's increasing over time. What? From the beginning or just the last part? Okay, the most common mistake that people make is thinking that the first year where nothing happens is year 0 instead of year 1. And so, like for example, sometimes if you see a cash flow diagram like this, sometimes the accident that people make is they say, well, here is 0, here is year 1, here is year 2, but really that's not true. Here is year 0, and this is year 1. And in year 1, nothing is happening because we say this is 0G, 1G, 2G, 3G, and so on. So that's the pattern. All right. So with that said, I would like you to go ahead and attempt question 2 on the back of the paper where we're talking about interpolation, and then take a look at the gradient as well. And I've got the solutions to those. I'll be circulating around as you're working on it. Yeah, just a minute. There it is. All right. The future value? Move everything to year 4. Yeah, so move the 200 to year 4, the 400 to year 4, everything. Yeah. Excuse me? Okay, great. Looks like that's the right answer. Problem 3. I think most of the students are getting stuck on problem 3, so let's just quickly make sure we're on the same page with the second one. All right. So you find the slope, 0.2085, and then multiply that by 0.3, which is the delta x, and so then that tells you this is how much you add to the factor that is equivalent to 8. So you want to find out what should be the factor for 8.3. It's going to be the factor for 8 plus some difference. And the difference is what you get by multiplying the slope of the line by 0.3. So here is the factor if you interpolate. And if you actually do it by calculating using the formula, then it should be 2.2197. And so you see it's fairly close. It's about 1% precision in this case to interpolate versus to calculate it directly. All right, let's look at the gradient. Okay, I told you that the pattern is that you have in year 1, you have 0G. Year 2 is G, then 3G and 4G. So what is the value of G? It's always increasing by 200, and so you should say G is 200, and in part A I'm asking you P is what? And so this is a problem, part A is a problem where you want to find P given G. So P slash G. You know, if we were going to summarize this problem in sort of the that bracket summary language that we've had before, it would be find P given G for I equals 8%, N equals 1, 2, 3, 4. Okay, so we have at the top of the page a table where you can find the P slash G column. Here it is, gradient present worth. Go to row 4, and you can look up the factor. It looks like it says 4.6501. So that's the factor of P to G. So then if you want to find P equals G times the factor. And that's how you can find the answer to part A. Okay? So here's the answer to part A. If you move all of that cash from its future dates into the present, then the equivalent is that in the present it would be worth 930.02. Okay? So try and do a similar thing with part B. In part B, there's an unknown and there's a known. There's a factor that you can look up, and the unknown you're trying to solve for will be the factor multiplied by the known. All right. That's right. Yep, F divided by G. Yep. No. Nope. It's going to be a different factor. It's not the same factor for part B, because it's going to be a yeah, but it is a F/G. The formulas are on the front. Okay, so for part B, we need to use the formulas because you don't have the factor. For part B, it is a F/G. Right? So you don't have an F/G there, but you do have it here. The formula for F/G. So let me just show you what it looks like. Okay, so on the front side of the paper, you can get the equation for F/G and calculate the factor by substituting in I and N into the formula. And so the factor, when you do all the substitutions, the factor is going to be 6.3264. So the future amount will be G times the factor. G is 200. The factor that you calculate is 6.3. And therefore, it is 1265.28. There is, by the way, there is a formula for F/G that, some tables you can look it up off of a table like this, but in this case, for arithmetic gradients, it's just doing P/G and A/G. So if you want to do it to the future, you have to use the equation method. That wouldn't work. Well, you probably moved all of them individually then, right? Each time? Multiple times? One time? I'd have to take a look at that, but I don't think it's going to work. Because you're not taking a single amount. You're taking 200 to there, you're taking 400 to there. All right, so we're done for today. Hope you have a great weekend. Let's just take one last look at the announcements. Remember the main thing, we're going to meet in the other classroom on Sunday. So I'll see you then.